or approximate measurements as such. Okay, so let us first look at what is a what is a measurement in general. Okay, forgetting about quantum or classical or whatever, how do we even define what is a measurement? So the idea is we have some system. Okay, we have a system. Okay, and we want to probe this system somehow. Okay, so we have a system and we want to probe this system for some of its outcomes. So we want to, for example, I have a car. Okay, and somebody wants to know what is the speed of my car. That could be one of the probe. Okay, they can have a camera, speed camera, then they can figure out, okay, that is the speed. Or they want to know the position of my car, whatever the observable could be. We have a probe, some way of probing the system to get that particular outcome. Okay, how do we do that? So let's take a very simple example. Let's say I want to find out what is the position of a particle. Okay. Let's say I have some particle in some coordinate system. Okay. So what I do is I have a particle which is located somewhere here in my space. Okay. And I want to figure out what is the location of this particle. For example, let's say. Okay. So what I do is I first define a set of coordinate systems. Right. So I will have, let's say, an x-axis, which I generally call by x cap, and a y-axis denoted by y cap, and then I can define my origin as well. Okay. So now, how do we find out what is the position of this particle? We just look at the vector from the origin to the particle. Okay. We draw a vector there, and then look at the projection of this vector along the x-axis first. Okay. So let's say this particular point I can label it as x0. Okay. Next, what I can do is take a similar projection along the y-axis. Okay, and let me call this particular value at which it intercepts the y-axis as y0. Okay. So traditionally, I will say the particle is then located at x0, comma y0. So x0 here is the intercept of or the projection along the x-axis, and y0 is the projection along the y-axis. Okay. However, note what we have done here is, so some steps we have followed in order to find out the location of this particle. So the step one was we fixed a basis. Okay. So in linear algebra, we have this concept of a basis. Okay. Essentially, basis is defined by linear independence plus span. So all the vectors that I have in my basis set, they should be linearly independent. Moreover, they should span the entire vector space. So I will not go into too much detail. To people who are interested can look at linear algebra for that part. Okay. And this is a very important aspect in when we talk about measurements. We have to fix a basis. Okay. Classical, quantum, whatever, we have to fix a basis as we just did here. So we took the Cartesian coordinates, that was our basis, okay, and that was our first step. Secondly, what we did was we took a projection along the basis vectors. So we first took a projection along x cap, then we took a projection along y cap, okay, and the result of this projection then gave me the values x0, comma y0, which formed my location. Okay. However, note that the basis that we have chosen in general is not very unique. Okay. Even in mathematics, the basis that we have is not a unique vector set. Okay. Basis can be infinitely defined. However, the number of elements or the number of vectors in that basis set, they are fixed. The numbers are fixed. Okay. We can choose a very different basis as well in order to find the position of the same particle. So let me take a different basis now. Okay. So let's say we already have this x cap and y cap, okay, which was our earlier basis, and this was our particle. Okay. So what I can do is I can have a vector. Okay. I can look at its radial distance from the origin, okay, as well as the angle it makes from the x cap axis. So now I can define another basis. So this is my second basis, which is defined by this set of unit vectors r cap and theta cap. Okay, and what I can do is I can again take a projection along r cap and take a projection along theta cap and try and find out what is the position of the particle, and in this case it is somewhat known as like r naught and theta naught. So I follow the same strategy once again. I fix a basis, I take a projection along the unit vectors, and whatever the result I get, I report it as the location. In the second basis, note that the location is now different. Okay, it is no longer x naught y naught. It is now r naught theta naught in a different coordinate system. Okay, so here r naught theta naught. In general, the numerical values will not be the same. Okay, but here we note one thing. It is not the numerical values that we are actually looking for in a measurement, but rather some particular outcomes when we are taking the projections. Okay, how they are oriented along in a particular basis set. Okay, so this is something which is very intrinsic to performing a measurement, and right now we have not even imposed any quantum mechanics or anything, right? So let us try and come to the quantum scenario, because that is what the talk is all about. Okay, so let us try and generalize this set of or like the algorithmic way of implementing a measurement. How do we do that in quantum theory? Okay, so now the idea is, let us move to QT. Okay, and first we need to fix a basis. So step one, fix a basis same as before. Okay, and in this case my basis will no longer be set of unit vectors. Okay, in fact they will be cats, denoted by cats. Okay, so I can have a basis, let's say, denoted by cat e1, cat e2, and maybe up to cat en. So in this case I have a set of n elements, and this implies that the dimension of the Hilbert space that I will be looking at is n dimensional. Okay, so I have fixed the basis. Let this be a basis, and what I can do is, let's say I have some quantum state, let's say cat psi. Okay, what I will do is I will write this state in terms of this particular basis. So it is nothing, just a superposition of these basis elements, right? Very easy. Right now we have just taken a quantum state, written in terms of the basis elements. Okay, in as a superposition element. Okay, so let us for the moment only focus at n equal to 2. Okay, then we will generalize for arbitrary. Okay, so n equal to 2 means we have our state cat psi, which is c1 e1 plus c2 e2. Here there are a few points to be made, such that summation I mod ci square is equal to 1. So the state should respect the normalization as well. Okay, so this is required, and the coefficients ci, they are in general complex. Okay, they are complex numbers, they are not real numbers. Okay, so now let us again come back to the same approach. We have a coordinate system which is formed by our basis elements. Okay, we have the first element as ket e1 and the second element as ket e2. So remember, we are only looking at n equal to 2 for the moment. Okay, and then we have a vector. Let's say we have the vector ket psi. Okay, and then we now want to implement some sort of measurement on this ket psi, which is denoted by, the measurement is denoted by the basis that we have chosen in this particular basis. Okay, So we know what is the next step. The next step is we just take a projection along E1, take a projection along get E2. Okay. So this forms a vector. Sorry. This forms a vector which is taking a projection along get E1, and this forms another vector which is a projection along E2. Okay. So here P1, which is the projection operator, is nothing but get E1 E1. Okay. And P2 is P2 E2. So as you can see, these are projectors. Okay. So what they do is they will project onto the E1 basis or the basis element or the E2 basis element. So for example, if I am taking E1 and cross E1 acting on ket psi, what it will do is it will take the inner product of E1 and psi, and it will have some coefficient value and the state E1. So let us say E1 psi is, let's say, some value, let me call this as small E1. Okay. Then what I have is E1 get E1. So as you can see, the vector has now, after projection along the E ket E1 axis, but now it has an additional coefficient as well given by E1, which in general would be complex. Okay. Moreover, we also know that somehow the length of the projection, the length of P1 ket psi is somehow related to the probability of obtaining that outcome in quantum theory. Okay. So let's take one particular example. Okay. So let me take ket psi is equal to C naught ket 0 plus C1 ket 1. So here my basis is already decided by ket 0 and ket 1. So it's a two-dimensional Hilbert space, and my basis is defined by the computational basis set or the ket 0 ket 1 basis. Okay. So now I can define the projections along ket 0 as ket 0 0, which is the projection along ket 0 axis. Okay. And similarly, we also have projection along ket 1. Okay. Now let's see what we get once we apply this projectors onto the state ket psi. Okay. So let's first look at once we are projecting 0 0 psi along 0 0. Okay. So what will this give us is C naught 0 plus C1 1, right? And as you can see, we will have C naught 0 0 plus C1 0 1. Okay. Here we have an inner product with 0 and 1 and an inner product of ket 0 with 0. So this part is 0 because ket 0 and ket 1, they are orthogonal to each other. Okay. So this part will no longer play a role, and at the end of the day, what we have is just 0. C naught ket 0. And similarly, we can see if we do the projection along 1, we will just simply get C1 1. Right? And as I mentioned, the length of the projectors, the length of this vector, as well as the length of this vector, has something to do with the probability of obtaining this particular outcome. How so? How do we evaluate the length? We just look at the norm of the vector corresponding to the length, right? So here, once we have the vector C naught ket 0, I can find out its length by taking a norm. So I will denote the norm by these two vertical lines, and this is nothing but mod c naught square. Okay, and similarly the length of c1 cat 1 is c1 mod square, right? And to people who are somewhat familiar with quantum mechanics, they can already see, oh, this is the probability of obtaining the outcome 0 and this is the probability of obtaining the outcome 1. And this is how it comes. Like it has something to do with length. Although we have not yet defined how the measurement is taking place, how the basis, what the basis has to do with the measurement, but somehow things are falling into picture. We need to look at projectors. Okay, we need to project the state along the basis. Okay, and then try and finalize what is the length of the vector that we are getting, and somehow relate that with the probability that we are observing. Okay, so somehow we have this now concept, uh, at least in our mind. Moreover, the length of both of the projectors, that should sum to 1, and this is because the probability of obtaining the outcome 0 plus the probability of obtaining the outcome 1, that should sum to 1 because they are mutually exclusive and exhaustive. Okay. Now let us formalize the notion of what we mean by a measurement or a quantum measurement. Okay. So for this particular picture, many people have the idea that this equation A acting on cat psi is equal to A times cat psi has something to do with measurement. Okay. And I will show that, okay, this particular equation has absolutely nothing to do with measurement. Okay. So if you are familiar with this equation, I would request that you forget this equation for the moment. Okay, just forget it for the moment, and then we will talk about it later. Why it has nothing to do with measurement, even though many books, many textbooks, you will find that they always write this equation. This is nothing but an eigenvalue equation. Okay, so for the moment, forget that this equation exists. We will not talk about it for the moment. And once we have formalized the notion of a quantum measurement, then we will come back to it and see why it cannot capture the essence of a quantum measurement. Okay, so let us proceed. So in order to make a measurement, I will assume that there is a black box. Okay. Somehow there is a probe. I have a probe which is probing the system. I don't know how it is probing. Okay. Somehow it is probing. Okay. And I will see what I can get out of this probe that I have. Okay. So I have a black box. Oh, sorry. So let's say I have a black box. Okay. I cannot open this box. And I know that it has some input and some output. Okay. So in this black box, I will input my quantum state. Okay. Some input state. Okay. And I should get some output state. Right. Moreover, I can choose some settings. So I have many different settings to choose from. So for example, if I want to measure, let's say some observable sigma z, I can choose this particular, the first setting. If I want to measure, let's say sigma x or sigma y, I can choose the second setting. If I want to measure some other observable, then I can choose the other settings. So infinitely many settings are possible. Okay. However, I will just like draw a few of them. But as you can see, for every particular observable that you want to measure, I say there corresponds some setting, some button which we can press, and the black box will know, okay, then we have to measure that particular observable. Okay, so I have to choose a setting. Okay, by pressing some button in this particular device. Okay. Moreover, the device will output some information. Otherwise, it's not a measurement, right? The measurement should tell me, okay, this is the outcome you got, this is the probability with which you got, or whatever. It should give me some result. Moreover, the result needs to be classical. Okay, classical in the sense. So, for example, if I go to the lab and I perform an experiment, let's say with spin atoms with spin, and I have a screen. So what happens is I pass the spin atoms along some magnetic field, and I get fluorescence or maybe some detection at some part of the screen. Okay, so I note down, okay, at this part of the screen, I know this is the outcome that I get. So this part that I have noted down, that is now classical. Okay, for example, I can note down the position of the fluorescence or maybe the time of fluorescence or whatever. These are all classical variables now. They are no longer quantum. So the result of the measurement, even though it is a quantum measurement, is classical. Okay, so I will uh, make this outcome like a meter. Okay, a meter reading could be, for example, your position or maybe the time or whatever. Like it could be some meter which may have some continuous set of outcomes. It may have some discrete set of outcomes. It may have infinitely many or finitely many. Does not matter at this moment. Just that it is a meter reading that we have. Okay, so this gives me some classical outcome. Okay, so this particular thing denotes a classical outcome, and I will sometimes also call it as a meter or a meter reading. Okay, so this is very important to understand. We have some input state, so let me just mark them. So I have some input state which I will input to the black box, upon which I want to implement the measurement, the quantum measurement that I have. Okay, something happens in the black box. We are not conjecturing what is happening right now. We will do this in the later parts of the lectures. Okay, when we will try and open this black box. Okay, but for the moment we will not assume anything. Something is happening, some process is happening, and this process is happening corresponding to a setting that we have chosen. So corresponding to some observable that we want to measure, we have chosen a setting. Okay, something happens in the black box. We get some output state. Okay, and a classical result. Okay, so this is the formalism that we will be using to describe our quantum measurement. Okay, so here the input state that we have. So this is generally taken to be a quantum state get psi, upon which we will be implementing the measurement. Okay, and the classical outcome. So this is an outcome which tells me along which projection I have now implemented the measurement. So for example, remember we were choosing a basis and then we were projecting along cat E1, cat E2 or cat E3 and so on and so forth. Okay. So the classical outcome will tell me along which basis element I have now projected it. Okay. So for example, it will tell me a classical result corresponding to which cat E1, sorry, EI, the projection was implemented. So for example, let's say in the first run of the experiment, I have a quantum state, I put it in the black box and it projected it along, let's say along cat E1, for example. Okay. Then the classical result would tell me, okay, like some particular value would show up on the meter saying, okay, it was E1. Okay. Or maybe it could be a value red, for example. Okay. Or a value zero, for example. Whatever. This is just a label. This will just tell us corresponding to whatever value we have, this projection was implemented. Okay. And this is done probabilistically. So the black box somehow does this probabilistically. Sometimes it will project along E1, sometimes it will project along E2, E3, and so on and so forth. We don't know when it will project along a particular basis vector, but it decides that on its own. Right now, we will assume this part. Okay, this is probabilistic, and these labels they could be arbitrary, but they have to stay consistent. For example, you can have a label saying the outcome is zero, but it should always mean whenever you get the outcome zero, it projected along E1. You can have a different label corresponding to E2, E3 and so on and so forth, but they should remain consistent. Okay, so these labels, they are just there for our sake. Okay, for example, in our meter readings we can have electricity current, okay, corresponding to, let's say, 0, 1, 2, 3, 4, whatever our electricity is we are consuming. Maybe we are measuring position, we can have position there, okay, whatever. Okay. And then we have chosen an input setting. Sorry, the input setting basically chooses which basis are we using. Okay, are we choosing this basis, or are we choosing a different basis in which we have E1 prime and up to En prime? Okay, so whatever basis we are choosing, are we measuring the position of the particle? Are we measuring the momentum of the particle? Are we measuring the charge, or whatever? Whatever is our observable that we are trying to measure. Corresponding to that, we will have different bases. Okay, and finally, we will have an output state, which would again be some quantum state ket phi, and this state after measurement is in general not equal to the input state. So in general, ket phi is not equal to, oh sorry, ket psi. Okay, so the input state is in general transformed by the process that is happening inside the black box of a measurement that we have. Okay, so in general it is not the case that it will be the same. Okay, so let us now proceed and see what can we learn from this. So we know that once we have performed the experiment, the main quantity of interest, at least in quantum mechanics, is what is the probability of getting a particular outcome. Okay, so for example, let's say I am measuring, let's say the spin, like for example, in a Stern-Gerlach experiment, I am trying to find out, like I have a sigma z observable, which means the magnet is oriented along some axis z, and I'm trying to see whether I get spin up or spin down, and I'm just implementing that observable. So at the end of the day, I will be implementing this measurement on thousands of particles, and I will see, okay, like 500 of them gave me a fluorescence on the upper part of the detector, and 500 of them gave fluorescence, let's say, at the lower part of the detector. And then I will say, okay, the probability of getting a spin up was half, and a probability of getting a spin down was half. So at the end of the day, we are looking at statistics. We are looking at probability distributions over the outcomes. Okay. So the quantity of interest is probabilities. Okay. And how do we evaluate what is the probability? So it generally depends upon two things. Okay. So we know from the black box that we have developed, the outcome depends upon the outcome depends upon firstly what is the input state. Gets high. Okay. And what was the setting chosen? Basically asking what were we measuring, right? And the setting generally then corresponds to whether we are using the basis, let's say cat E1, En, or were we using a different basis. So let me label this basis as mean. Okay. So we know it just depends upon these two things. The output state that we get is dependent again on these two things. It generally does not describe the probability. So the probability will not depend upon what is the output state, quantum state that we are getting. In fact, the probability will only depend upon what we are inputting to the device. And there are only two inputs, the input state psi as well as the setting that we are choosing to perform the measurement. Okay. So in this case, we know that we can ask the question, okay, the probability of getting some outcome EI in the meter reading. Remember, we have the meter and we were labeling it as some variable EI or whatever. Okay. And we have to condition this. Okay. So we have to ask ourselves, okay, what was the input setting and what was the input state? Okay. So the probability of getting the outcome EI conditioned on the setting that I chose corresponding to, let's say, nu. Okay. As well as the quantum input state that I had. Okay. And Max Born gave us a very nice relation to evaluate this. And this is nothing but taking a trace over the projection operator corresponding to the outcome that we had EI, okay, EI, and an inner product of psi psi. Okay, so this entire thing is known as Bond's rule. So this way of evaluating probabilities in quantum theory is known as Bond's rule. It was given by Max Born. Okay, we will not go into how he derived it. It was more of a pedagogical way of doing things, but we will not go into that part. So it was just given by Max Born, and we can see that it also relates to some of the already well-known examples people might be aware of. So let's first look at how it can be related to the usual expectation values that we are observing and so on and so forth. So let me just open this trace. Okay. So we have this quantity EI, right? And what I want to do is I want to open the trace, and in usual bracket notation, this is generally done in this particular manner. So in this basis, I will open the trace. So I will have EJ, right? So here, notice what I have done is I have taken the same object that I had and sandwiched it between EJ and taken a sum over EJ. Okay. So this is equal to, so this particular quantity gives me delta Ij because they are orthonormal to each other. Okay. And this gives me EI psi psi EI, right? And now again notice that I have two scalar quantities, the first one and the second one. Okay, since they are scalar, I can move them around. So what I do is I just take this quantity, move it around here. I take this quantity and move it back here. Okay, so what I get is psi EI EI psi. So I just took the second quantity, this one, moved it to the front. The first quantity, which is again a scalar quantity, I moved it to the back end. Okay, and now as you can see, the projection EI is now sandwiched between psi psi. So this is, I can write it down as some projection EI and sandwiched between psi psi gets out. Okay, and to people who are already aware, this is nothing but the average value or the expectation value of the projection PI. So this is the expectation value of PI. Okay. So let us take a few examples how the quantum measurements work. Okay. So let us take an example where let us take the initial quantum state as get psi equal to 1 by root 2, get 0 plus ket1. So this quantum state is an equal superposition of ket0 and ket1. Okay, and let us choose a setting which is corresponding to the observable z. Okay, some setting right now. Okay, forget I said the observable z. So some setting I am choosing, and I want to measure it in the basis of ket0 and ket1. Okay, so I have ket0, ket1. Okay, corresponding to this setting, I can now find out what are the projections. They're nothing, just taking an outer product of the basis elements 0 0 and 1 1, right? Once I have taken the projections, then what I need to do is I need to find out, okay, what is the probability of getting the outcome 0, condition that I chose the setting as z, and the input state was ket psi. Okay, so this is, as you can use Bond's rule, 0 0 psi psi, right? And if you evaluate this, you will find you will get equal to half, which is nothing but taking the coefficients that we have and then squaring them. Okay, we general audience might know that whenever we want to find out what is the probability of the outcome 0, we just take the coefficient corresponding to that and then just square it. But this is the underlying phenomena where it comes from. You take the projection and then look at the length and then we try and relate it to the probability. Moreover, I can choose a different setting for the same state. So I can choose a setting X where now my outcomes or my basis is now somewhat different. I have a different basis. Okay, here ket plus is nothing but a superposition state of 0 and 1, and ket minus is the orthogonal complement of this. It's ket 1. Okay, and in this case, we can also ask what is the probability of getting the plus outcome. Condition I chose the basis setting as Z, and my state was ket psi. So I am still taking the same quantum state ket psi. Okay, so in this case, we can again apply the Bond rule, and now we will have the projection plus plus thing on psi psi, and as you can see, this will just give me equal to 1. Okay, and moreover, the probability of getting negative eigenvalue for the same setting and the state ket psi is then the prob 1 minus the probability of getting the outcome plus, so which is nothing but 0. Okay, so now we have looked at how to formalize the black box. Now what we can do is we can now formalize what it means to have a projective value measure. Okay, so at least now we can look at what do we mean by a projective value measure. Okay, projective value measure. So we will say that we have a projective value measure, or we are implementing projective measurements or orthogonal measurements when we have a set of projectors denoted by pi I, okay, or denoted as such. So I have a set of them, okay, could be infinite, could be finite, no matter. The idea is that I have a set of projectors such that they satisfy a few criteria. Okay, so the first criteria is pi I should be greater than equal to 0. Okay, this should be true for all outcomes, and this actually corresponds to positivity in the sense that the probabilities that I should get in my outcomes, probabilities are positive. If the projectors are not positive, then the probabilities that I would be getting, they are not confirmed to be positive at all. Okay. Secondly, I require that the sum over all the projectors it should sum to the identity matrix. Okay. What this means is that the probabilities should sum to 1. So this is a fact of mathematics, that if I have a set of mutually exclusive and exhaustive set of outcomes, then the sum of all the probabilities for these particular outcomes, it should sum to 1. So for example, if I have a coin and I am tossing the coin, then the probability of getting heads plus the probability of getting tails sums to 1, right? So this is exactly what we mean by this particular relation. When we are summing over all the projectors, they should sum to identity matrix. Okay. Sometimes this relation is also called as the completeness relation. And thirdly, we also require that they should be valid projectors. They should be orthonormal projectors. Okay. So this condition translates into pi I, pi j. So if I take the product of two projectors, pi I and pi j, it should give me delta ij pi I. And this condition is what we will call as, sorry, orthonormality. So when they are orthogonal to each other, when pi I is orthogonal to pi j, I will get the value 0, where delta ij will just give me 0. But if I is equal to j, delta ij would be just equal to 1, and then I will get the same projector pi I. And this is by fact that pi I square should be equal to pi I. Otherwise, it will not be a valid projector. Okay. So these are the three conditions which tell us when a set of vectors or projectors, they are forming a valid measurement. Okay. So we will call them as conditions for PVMs. Okay. And here, as you can see, what we have done is we started off with the basis. We fixed a measurement device. Okay. Although we have not opened the device, we figured out what is the probability to get a projection along one of the basis elements, E1, E2, and E3, and so on and so forth, and what are the different outcomes we can get, as well as the probability of getting the different outcomes. Okay. Next, as I promised, let us look at the equation that people are generally more aware of. So sometimes in textbooks, it is written that the condition that but this particular equation, a psi is equal to small a psi, is a measurement of the observable A. Okay. So right now we have not talked about any observable. Okay. We have only talked about choosing a basis and implementing a measurement corresponding to that basis. How do we relate this to a particular observable? So let's say I give you the observable sigma z. How do we implement a measurement of sigma z on some particular quantum state psi? And generally in textbooks, it is written that this is the way to implement the measurement of the observable A on the state psi. However, note this is an eigenvalue equation. Okay, and that's what it is. This is just an eigenvalue equation. Let's say I give you some state at phi and I ask you to implement a measurement of the observable A on this particular state. And moreover, I say ket phi is not an eigenvector of the observable A. Then how will you implement the measurement of the observable? Okay, so this equation does not tell us that, right? Moreover, this equation does not tell us what is the probability of getting the outcome. Okay, as we looked at before, the probabilities are what are fundamental. The probabilities or the statistical distribution, that is what we are looking for. And this equation does not tell us that. Okay, so for an example, look at, for example, the poly sigma z matrix, okay, which has eigenvectors denoted by ket 0 and ket 1. Okay, so what I can ask is, okay, if I want to measure sigma z on ket 0 following this eigenvalue equation, I will get something like plus 1 ket 0 sigma z acting on ket 1 minus 1 ket 1. Okay, but what if I want to implement a measurement of sigma z on the state How do I do that then? Right? So now we have a superposition state, and we already know that this particular state is not an eigenvector of sigma z. However, we also know that if I were to implement a measurement of sigma z on this particular state, I will get the outcome get 0 with probability half and outcome 1 with probability half. So where did that knowledge come from? Right? So if there is one thing you can get out of this faculty development talk, uh, it should be this, that this particular equation that we have, which is many times written in textbooks, this is just an eigenvalue equation. It will just help you evaluate what are the eigenvectors and what are the eigenvalues corresponding to some observable, and that's it. That's all the help it can give you. It does not describe a quantum measurement. Okay, this is not a quantum measurement. Okay. Now the question is, I want to implement a measurement corresponding to the observable sigma z. How do I do that? With the already developed understanding that we have for projective value measures. How do we do this then? Okay. So the idea is very simple. So let's take a particular example and then work through how do we do that. Okay. So let's take the example. Let's say the observable that I want to measure is sigma z, and I will just write down sigma z. How it looks like is 1 0 0 minus 1, right? So the first step is find eigenvectors and eigenvalues of sigma z. Okay, this is the first step. How do we do that? We use the same eigenvalue equation. Okay, we use this equation. Using this equation, we find out what are the eigenvectors and the eigenvalues of sigma z. Okay, once we have done this, I am now skipping the step. So the eigenvectors we will find as ket 0, ket 1, and the eigenvalues corresponding to these eigenvectors as plus 1 and minus 1. Okay, so plus 1 eigenvalue corresponds to ket 0 and minus 1 eigenvalue corresponds to ket 1. Okay, the second step is, now we have a set of eigenvectors. This forms a basis. We now go back to the same understanding that we have developed, how to implement projective value measures. So now we have a basis corresponding to these eigenvectors. We just take the projections corresponding to them, 0 0 and 1 1. Okay, now once we have the projections, we now have an understanding how to evaluate, how to do a measurement for this one. Okay, and this forms my setting in the same measurement device, the same measurement black box that we had. And what we can do in the third step is find out what is the probability of getting the outcome 0, provided that I chose sigma z and some state which we have not yet specified. Okay, could be any state. Okay, and then we can find out what is the probability of getting outcome 0 and the probability of getting outcome 1 as well. Right? So here we now want, once we have found the probabilities, we want to find out what is the expectation value of sigma z. Okay, this is in general what is taught in many textbooks. They want to evaluate the expectation values of some observables. Okay, and the way we do that is, we first note that I can write sigma z. So this is again a very nice result in linear algebra, where any observable can be written in terms of its projectors, eigenvectors as projectors, as well as a combination using their eigenvalues. So what I need to do is, I will just multiply the corresponding eigenvalues with the corresponding eigengets in terms of projectors, and this will give me the observable sigma z. Okay, so I have plus 1 multiplied by 0 0 and a negative 1 multiplied by 1 1 get 1 1. Okay, so this gives me the observable sigma v, and this is true for all observables in any case. So this is the result in mathematics. Okay, so something which we are not going to prove. Okay, so now what I want to do is I want to evaluate the expectation value of sigma c. So this is nothing but an expectation value of 0 0 minus 1 1. Okay, and since expectation values are additive, I will just open them. Okay, and I have this particular equation, and we already saw that the expectation value of 0 0 is nothing but the probability of getting the outcome 0 for some state xi minus the probability of getting the outcome 1 for the same state xi. Okay, so this is something which we can evaluate from the Bond's rule, as we have talked about, given some quantum state psi. Okay, moreover, the probability that we can evaluate is true for any arbitrary quantum state. Could be a mixed state, could be a pure state, whatever quantum state, the trace rule still holds. Okay, so it could still be 0 0 rho. Okay, so using this particular uh, equation, we can then evaluate what is the expectation value of the observable sigma z. Okay. So here we have now looked at what we call as projective value measures. So maybe I can just stop at this particular point and ask if there are any questions regarding this before we move on to positive operator value measures or non-orthogonal measurements. So are there any questions up to this point? So the last equation is this, and here we are assuming that the Born rule that we have. So let me just rewrite the Born rule. So the probability of getting some outcome 0 sigma z for some pure state psi, we wrote it as the trace of 0 0, which was the projection corresponding to the outcome 0 that we had. Okay, and then what we were doing, we were just taking the product with the pure state psi, right? So this was the usual Born rule, but this is a pure state. Okay. However, we know that pure states are not the most general kind of states. We can have mixed states as well. Okay. And in that case, the rule does not change. Okay. Instead of putting the pure state in this formula, we will just put some mixed state. Okay. Inside it. And if you are given some mixed states, we can now have the probability of obtaining outcome 0 given some mixed state rho. So here rho is a mixed state. So does that answer the question? Ah, wonderful.
Is there any question of the participant? So I think, sir, we can take a 5 minutes break if you.
Okay, sure. So let's take 5 minutes break, and we can resume. Let's say at 3:58. We can resume at 4:03.
Yeah, definitely sure. So all
Sure.
participants are requested to take a break of 5 minutes. We will resume at 4:03. Okay, thank you.
Shall we begin?
Yes, please, we can resume the session.
Okay. So now we have looked at projective valued measures where we were taking an orthogonal basis, an orthonormal basis, and now we will move on to the positive operator valued measures. In which we will take a non-orthogonal set of basis elements, and our outcomes may in general not be corresponding to some. Okay, so let me formalize the idea first. Okay, so let us again go back to the idea of a measurement. Forget again quantum, classical, or whatever. So how we were doing that? We were choosing a basis, a coordinate system. Okay, so we had chosen an orthonormal basis. We had kept E1 corresponding to some basis element E1 and in another basis element ket E2. And we had a quantum state, say ket psi. Okay, and the idea was that we take a projection along ket E1 and a projection along ket E2. And that was the idea of the projective valued measures that we had. Okay. However, as I mentioned, what we want to do is we want to fix a basis. Okay. So ket E1, ket E2 forms a basis. However, that is not the only basis that we can have. So remember what is a basis? We need to have linearly independent set of vectors as well as they should span the entire vector space. Okay. Nowhere it says that we need to have an orthogonal set of basis elements. Okay. So what we can have is something different. We can choose a basis vector set as something like we can have a vector corresponding to this one. Let me call this as ket E3. Okay. And we can choose ket E1 as the second, let's say, or the first basis element. So now my new basis corresponds to ket E1, comma ket E3, such that the inner product between E1 and E3 is in general not equal to 0. So they're not orthogonal to each other. Okay. And the idea of the measurement remains the same. Okay. We have a different basis in which the elements, they are not in general orthogonal to each other. And what we will do here is we will again take the projection along E1. Okay. And then we will take a projection along E3. Okay. Whatever that projection value is. Okay. So the concept of the measurement does not change, just that the results that we will get or the entire outcomes that we will get, they will change. So here, as before, we know that the projection vector that we get in this case is denoted by E1 acting on ket psi. Okay, and on this case, when we have ket E3 as our second basis element, we will have the projection as E3 acting on ket psi. Right, so this will be our basis, and then what we can do is try and see how we can implement this quantum measurement. So in this case, in general, what we have is we have a basis ket E1, ket E2 up to, let's say, ket En. Okay, and corresponding to these vectors, we have chosen in them in such a way such that Ei, Ej, sorry, this is in general not equal to 0. The inner product between ket Ei, ket Ej is in general not 0. Some of them may be orthogonal to each other, but in general they are not orthogonal. Okay. How do we implement such a measurement? Okay. So first let us see how do we physically even implement this measurement based on the information that we have about implementing projective measurements. So right now we will assume that the device that we had for implementing projective value measures, we can implement that device. Okay. So we can go to the lab, we can implement that particular device, even though we have not opened it, it is still a black box to us. But let us assume that that can be done. If that can be done, how can we implement such a measurement? Because that particular device was dependent on the fact that we have orthogonal basis sets as our outcomes, as our basis. Okay. So here we will have an extended black box. Okay. So it would look something like this. Let me just draw it. So we have a box, okay, such that it can implement two different projective measurements. So this black box has two black boxes inside it. Okay. So this is black box one, which implements a measurement corresponding to a fixed setting mu1. Okay. So remember we already had the settings fixed. Okay. But here the black box inside the bigger black box is already fixed, has a fixed setting. We cannot choose the setting. Okay. We have already fixed it. Similarly, it has another black box corresponding to some projective measurement for the setting mu2. Okay. So mu1, this black box will have several outcomes. Okay. This black box will also have several outcomes. Okay. And what we do is we now introduce a randomizer or a box or a process which is random. So what is this? It could be a coin toss, it could be a dice throw, whatever. Okay, some process which gives me some random outcomes. Okay, so I can have different outcomes with different probabilities. This need not in general be a quantum random number generator or whatever. Some process which gives me some random outcomes could be a coin toss, like literally a coin toss, does not matter. Okay, so here with probability p, so this is a coin toss. Okay, and which I denote by p cap. So with probability p, it will tell the bigger black box to implement the projective measurement corresponding to setting mu1, and with probability 1 minus p, it will tell the device to implement the projective measurement corresponding to mu2. Once it has implemented one of these measurements, we get one of the outcomes. Okay, and then we report that as the particular outcome. Now, this all is inside the black box. What this means is that the coin toss, the results of the coin toss are not known to us. We don't know whether the coin toss yielded a head or a tail. In other sense, we don't know whether the measurement corresponding to mu1 was implemented or the measurement corresponding to mu2 was implemented. Okay, this is our lack of knowledge. In one particular instance of the measurement, one particular instance of the experiment, there would be one particular measurement either corresponding to mu1 or mu2. Okay. However, we don't know. It is our lack of knowledge that whether mu1 was implemented or mu2 was implemented. Okay. And as before, we will have an input quantum state, an input port. Okay, in which we will have our input quantum state and an output port which will yield our output quantum state. So in this port we will input our quantum state, and out of this one we will get some output state. Okay, so here let me remind this again. With probability p, mu1 is implemented, and with probability 1 minus p, mu2 is implemented. Okay, information about which of these measurements was implemented is not known to us. It is inside the black box and we cannot open the black box. Okay, so let me also label this as an important point. Information about which measurement is not known. Okay, so now what we can do is we can have several different outcomes and we can label the outcomes by some variable, let's say E0, E1, E2 and so on and so forth up to En minus 1. Okay. So these are the outcomes that we are going to get, not the classical outcomes, but rather corresponding to the classical outcomes. Earlier we had projectors, we now have some operators. Okay. So remember, in our non way of implementing the measurement, a vector corresponding to E3, okay, which was not orthogonal to E1. So there will be some observable or some operator corresponding to this basis element that will be giving us the corresponding outcome probabilities. Okay, we have not yet fully described what this operator or observable would look like. Okay, so corresponding to each of the outcomes, we have an operator E0, E1, E2 up to En minus 1. So as before, following the usual notion of a measurement, we require that the operators that we have, they should be greater than equal to 0, okay, corresponding to positivity, such that the probabilities that I will obtain, like later on in my experiment, they should be positive. By definition, probabilities should be positive. So this is ensured by having these operators as positive. So here I would also like to mention, like when I say that the operators should be positive, what I mean is that the eigenvalues, all the eigenvalues for this observable, they are all positive. Okay. So this is the meaning behind saying an operator is positive. All its eigenvalues are positive. Okay. Furthermore, so this is condition 1. I also require that the sum over all these operators ei, it should sum to identity, same as before, right? And we term this as completeness, and this is required because the probabilities sum to 1. Okay, so if I have 4 outcomes in my experiment, the probability of getting the outcome 1 plus the probability of getting outcome 2 and so on and so forth, it should all sum to 1. Okay, what this means is, in an experiment I will get some result. Okay, it could not be the case that I am not getting any result. So for example, in some photonic experiments, what can happen is that my detector does not click. Okay, that in itself is a result that the detector did not click. Okay, so you also have to take all these error noises into account as well. Okay, and once you do that, then you will have more number of outcomes. So let's say if you had two detectors. If the first detector does not click, that is another outcome. If the second detector does not click, that could be another outcome. Okay, so here we have this. Okay, but we have not yet defined what these operators EIs will look like. Okay, how are they even related to each other, and why are we looking at some operators instead of some projectors? Okay, why not look at projectors? Okay, so let us try and see what they should look like. So here I have some information about them. Okay, just by looking at the black box device that I have, I can have some information about them. I know with probability p, the measurement corresponding to mu1 will be implemented, and with probability 1 minus p, mu2 would be implemented, right? So let us assume there are only let's say 4 observables, 4 such outcomes labeled by e1, e2, e3 and e4. Okay, then we can generalize to n as well. Okay, so we know that I know that if E1 corresponds to E1 and E2 correspond to outcomes from the first measurement corresponding to mu1, and E3 and E4 correspond to measurements from the second measurement mu2, then from their completeness relation, I know that E1 plus E2 sums to 1 identity, and E3 plus E4 also sums to identity. right? But E1 and E2 are only observed with some probability, right? Because we are not always implementing the measurement corresponding to mu1. We are only implementing it with some probability p, right? So what this means is, in our mathematics, this is equal to p times identity, and the other one is equal to 1 minus p times identity. And as you can see, if I now add them all up together, corresponding to completeness relation, I will still get identity, right? Moreover, we can again simplify them. We can say, okay, corresponding to mu1, my outcomes would have been, let's say, corresponding to the projectors 0, 0, 1, 1. And corresponding to, let's say, mu2, the basis would have been, let's say, plus, plus and minus, minus, right? So here, what is happening here is, with probability p, I will be implementing mu1. With probability 1 minus p, I will be implementing mu2. So the entire set should look something like this particular value. So p times 0, 0, p times 1, 1, 1 minus p times get plus plus, and 1 minus p times get minus minus, right? And then we can generalize depending upon what sort of measurement we are looking at, what are mu1 and mu2 that we have chosen, and how we are modeling the device. Okay. So here again, we again need to look at the quantity of interest is the probability distribution or the statistics that we can get in the measurement. Okay. And distribution that we can get here is the probability of obtaining the outcome corresponding to EI. Okay, given that I have chosen some setting in the bigger black box. So I can choose some setting here as well. And these settings would correspond to choosing what are the projected measurements mu1 and mu2 here. Okay. Whether mu1 is, let's say, corresponding to a measurement along sigma z, or mu2 is corresponding along to sigma x, or whatever observables we are choosing corresponding to mu1 and mu2, that we can choose by choosing a setting here. Okay. But which measurement was implemented in one particular instance, that information is still not known. Remember that we can choose what is being measured corresponding to mu1 and mu2. There might be other as well, not just two. So we can have mu1, mu2, mu3, each of them being implemented, let's say, with some probability p, p1, p2, p3, and so on and so forth, right? And but we don't know at which instance which of these measurements is taking place. That is removed from our knowledge. Okay, we can select whether we are implementing sigma z, sigma x, sigma y, or whatever be the observable corresponding to mu1, mu2, mu3, and so on and so forth. But which one is implemented, we don't. Okay, so this is very important. Okay, and I'm just taking a very particular example where we have just two of them, mu1 and mu2, just to motivate what is happening here. Okay, so we can have more number of measurements, which will give us more number of outcomes, more number of operators EIs. Okay, but the math corresponding to it or the technique corresponding to it does not change. Okay, then we can look at what is the probability of getting the outcome EI, provided I chose the setting mu. Okay, and mu implies that I will be choosing mu1, mu2, up to mu and whatever we have, right? And we have some input state which could be in general mixed state. Okay, rho could be a pure state as well, does not matter. Okay. So this is again given by the bond rule. So we take the operator EI. Okay, let me just use a different notation for EI here. This is confusing because EIs are operators and this is just a classical outcome corresponding to the operator EI. Okay, so this is equal to trace of EI times rho. Okay, and as you can see, this is again once again the Bond's rule. So the Bond's rule does not change; that is constant. Okay, just the way we are evaluating the probabilities now corresponding to EI, as you can see, we now have EIs which are in general not projectors. So if you look here, for example, we take EI equal to P times 0, 0. This is no longer a projector now. Okay, because if it were a projector, then I can take EI square is equal to P square 0, 0, and this is not equal to EI. So this is in general not a projector. Okay, but the way we are evaluating the probabilities again is given by the Pons rule. Okay, let us look at a few examples. Okay, so here let me say that I have the measurement. Let me call this as mu. Okay, and the outcomes that I can get, or the way that I am representing the measurement corresponding to these operators EIs, is just given by P times 0, 0, P times 1, 1, 1 minus P times plus plus 1 minus P times minus. Okay, and now we are looking at an example. Okay, and trying to see how they are different from projective value measures. Okay, so here we have this measurement, and let us take the initial quantum state or the input quantum state as 0, 0. Okay, then we can ask what is the probability to get the outcome corresponding to E1. Okay, mu rho. So this is corresponding to E1, E2, E3, and E4. So we have 4 outcomes, and this entire operator I am labeling it as E1, E2, capital E3, and capital E4. Okay, so this is nothing but, again, using the trace rule. I will not write that down again, but you can evaluate it. This is equal to the value small p, whatever the probability p is here, equal to this value p, whatever value we are choosing. Okay, moreover, the probability to get the outcome E2 rho is now 0. You can again do this. Okay, the probability to get E3 mu rho is now 1 minus p by 2, which is again equal to the probability of E4 getting mu rho. So look here what is being happening. Let's try and analyze this particular very simple looking example. Okay, we have a pure state 0, 0. Okay, had we implemented the measurement corresponding to sigma z, which was implementing this particular measurement, right? What we observed was that the first outcome corresponding to 0, 0 always clicks. So the probability of getting the outcome corresponding to 0, 0 is 1. Okay, but look what is happening here. The first operator or the first observable outcome that we are getting in this uh, bigger one, capital mu, is p times 0, 0. Okay, and the probability that we are getting corresponding to this particular outcome is now given by this small value p. Okay, and moreover, we also get the other outcomes as well. It is not the case that only one of these outcomes are clicking always. With some probability p, the first outcome clicks, and with some probability 1 minus p2 p by 2, the third and the fourth outcome clicks. The second outcome although never clicks. Okay, so this is the difference between having a projective measurement and a non-orthogonal or a positive operator value measurement. Moreover, when we were talking about projective value measures, corresponding to each measurement, we could go to an observable sigma z, as I showed you, right? But for corresponding to each POVM, we don't have an quantity something like an observable. Okay, this is only a measurement. There is no observable corresponding to this particular settings that we have chosen, even though these measurements are the ones that will be taking place in the experiment. So what is happening in the experiment? When you perform an experiment, there will always be some noise, right? If there is noise, then you cannot have exact projectors, right? Because for projectors, you require that the operator 0, 0, if I square it, it should be again equal to 0, 0. But in experiments, this is not always possible. There will always be some noise, and if there is noise, that means this is not always equal to this quantity, and that means they are not projectors anymore. Moreover, they will not be orthogonal to each other. Okay, and as soon as they are not orthogonal to each other, you end up in the regime of implementing a positive or a non-orthogonal measurement or a positive operator value measure. Okay, moreover, let's say if we are implementing some measurement on photons. Okay, what is happening is I implement a measurement, some measurement on a photon. The photon is then lost. I don't get any output state. The photon is just absorbed. So in this case also, this is no longer a projective measurement. Okay, because we are not projecting the state of a photon onto some particular basis element. The photon itself is gone. So that cannot be a projective value measure. That again falls into the class of being a positive operator value measure. So in reality or in an actual experiment, we will not be implementing any projective value measures. They are theoretically ideal measurements. What will be happening in the lab is much more closer to being a positive operator value measure or a non-orthogonal measurement. As we will see in the subsequent lectures as well, when we try and open the black box, we can get many different sort of measurements as well. So people might have heard about weak measurements or non-demolition measurements and whatever. All those can be implemented using positive operator valued measures by getting different models of them, by modeling how these measurements are happening. So this particular black box that I have shown you here, which was implementing mu1 and mu2. This is just one model. Okay. There are many other models which can explain the same thing. Okay. The idea here is that the operators that I have, EIs, they should only respect one and two conditions corresponding to positivity and completeness. There can be as many number of outcomes as we require, and the only condition is they should be positive and they should complete to 1. So there is one question, what is mu1 and mu2? So mu1 and mu2 are the settings chosen for implementing the projective value method. So in the bigger black box corresponding to POVMs, we are implementing many smaller projective value measures, and the setting corresponding to those projective value measures is mu1 and mu2. Okay, so here we can choose mu1 as this particular basis or this particular setting, and mu2 as this particular setting. This is just an example that I am taking. Okay. So the idea is that these COBMs, they are quite unique in the sense that we don't require any orthogonal basis to implement them. Moreover, they are more closer to in real life applications. The measurements that you will be making in the experiments are more closer to being positive operator value measures. But the question is, if they are only coming from noise or any imperfections in my experimental device or whatever, are they even useful to study? Even though like it is very good to study them because they are more closer to the real life statistics, but do they have some advantage over projective value measures or not? Okay, and that is indeed the case. They are much more advantageous in certain information processing tasks than the projective value measures. So one of these tasks is the task of quantum state discrimination. Okay, so I will explain the task and then we will look at it from the point of view of a projective measurement and a POVM. Okay, so the idea is that we want to distinguish between two quantum states, ket psi and ket phi. Okay, I am given two quantum states, ket psi and ket phi, and I want to tell in one single shot whether the state I am given is it ket psi or is it ket phi. Okay, I don't know what state is given to me, yeah, but I know it is either ket phi or ket psi, and I want to distinguish between them. Okay, so let us first take the case when psi and phi they are orthogonal. Okay, so let's say for example, what I can take is cat psi equal to, let's say, cat 0 and cat phi equal to cat 1, right? And I am given one of these quantum states. I don't know which one, and my task is to figure out whether it is cat 0 or cat 1. Okay. So what I can do is I can design a measurement which is a projective value measure. Okay, and I can choose the setting mu1 equal to 0 0 and 1 1, right? So this is my measurement, and what I do is I am given one of these states and I just implement this measurement. Okay, if I get the outcome corresponding to 0, I know the state is sorry, cat psi. If I get the outcome corresponding to cat 1, I know the state that was given to me was cat phi. Why? Because if I was given the state cat phi, I will never get the outcome corresponding to 0 0 because they are orthogonal to each other. There is no projection, no value of projection along the basis element 0. Okay. Similarly, if I am given the state cat psi, there is no projection value along the basis element cat 1. So I will always get the outcome corresponding to 0. And I will know, okay, this is the state that I is given to me. So for orthogonal states, the task is very easy. It is very tricky. I can perfectly distinguish between the two quantum states very easily. Okay, within a single shot. I don't need to repeat the experiment again and again. You give me one instance of a quantum state, just one copy of a quantum state, and I can tell you whether it is cat psi or cat phi. Okay, again, I am assuming like all my experiments are ideal, but that is fun. Okay, theoretically that is fun. Okay, but what happens if psi and phi they are not orthogonal? Okay, so they are non-orthogonal states, and I want to distinguish between these two quantum states. How can I do that? Right. So the way to do that is now slightly trickier. Okay. So let us assume that the states that are given to me is, let's say, cat psi is cat 0 as before. Okay. But now assume cat phi given to me is something like cos theta cat 0 plus sin theta cat 1. Okay. So for arbitrary values of theta, we generally have that the inner product between them is not equal to 0. Right. Now, if I choose the same setting, so let me try like, okay, maybe I don't change anything. I just use the same setting as before and see whether I would, how best can I do? How best can I distinguish between these two states? Okay. So I use the same setting mu1, which is a projective value measure 1 1. Right. So now let's say if I was given the state taxa, right? Then I know the outcome corresponding to 0 will click. Okay. But if I am given the state cat phi, there is with a probability cos square theta, I will get the outcome corresponding to cat 0. And with probability sin square theta, I will get the outcome corresponding to cat 1. Okay. So let us see what is happening from my perspective as an experimentalist. It is my idea to implement this measurement corresponding to mu1 on some state which is not known to me. Okay, so I get some state. I don't know whether it is cat psi or cat phi. I implement the measurement corresponding to mu1, and I get the outcome 0 0. Okay, I cannot say whether it came from cat phi or cat psi. I don't know. Okay. So if I get the outcome 0 0, I will say I don't know. It could have come from cat phi or cat psi because both of them have some component along 0 0. Okay. But if I get the outcome corresponding to cat 1 1, then I can definitely say that it came from cat phi because cat psi will never give me the outcome 1 1. Only cat phi will give me that particular outcome. So in this case only I can say that the state is cat phi, right? Now the point here is I wanted to distinguish between cat psi and cat phi in one single round, and using this projective value measure I am not able to do that. I can only tell you when one particular outcome clicks that the state is cat phi, but I will never be able to tell you when I am getting the state cat psi. I will never be able to do that using this particular measurement. Okay. However, if we go to POVMs, if we develop some positive operator value measures, then we can do this. Okay. So what we are going to do is we are going to use a measurement which will have three outcomes: E0, E1, and E2. Okay. Such that the outcome E2 or the operator E2 is identity minus E0 minus E1. So remember we have the completeness relation E0 plus E1 plus E2 equal to identity. Okay, and using this completeness relation I will just write down the last outcome that I have. Okay, we are now left with defining what is E0 and what is E1. Right? So I want to design this particular measurement. So what I will do is I will say E0 is 1 by 1 plus S. So S is some parameter here, okay, which I will come to later on. It has some particular value, but for the moment we will treat it as a parameter S, okay, some parameter S, okay, and I have a projector pi 0 perpendicular, okay. So what this pi 0 perpendicular is, it is nothing but cat 1 1. Okay. Moreover, as you can see, for the state psi and phi given to me in this particular fashion, I am choosing the pi 0 perpendicular as the state which is perpendicular to cat psi. Okay. So this is nothing but a state which is perpendicular to psi. Right. Moreover, I can choose E1 as again 1 by 1 plus S. So remember, S is just some parameter that we will talk about later. Okay, and I will use pi 1 perpendicular, and as you may have guessed, pi 1 perpendicular is nothing but the orthogonal complement of the state phi. So the state phi that I am giving, I am given, I will choose a state which is orthogonal to this particular state, phi perpendicular. Okay, so what is phi perpendicular? It is nothing but minus sine theta cat 0 plus cos theta cat 1. Okay, so now I have chosen uh, E0 and E1, okay, in such a manner that E0 is directly proportional to the projector which is orthogonal to the state cat psi, and E1 is directly proportional to the projector which is now perpendicular to the state cat phi. Okay, so in this case let us see what we get. Okay, so here the probability of getting the outcome corresponding to E0, which tells me okay that I got a click corresponding to capital E0, okay, is given by trace of 0 0 E0, okay, which is 0. So this is in the case when when the state that I was given was cat psi. Okay, so when I am given the state cat psi, oh sorry, so when I am given the state cat psi, this is the probability that I can get, right, for the first outcome. So I will never get the first outcome in my experiment. Okay. Furthermore, I can also see what is the probability of getting outcome E1. Okay, and without doing any calculations, I will just write down as 1 by 1 plus S. and it will be AS of 0 0, and we have E1 here, right? So it is some particular value. Okay, we don't need to evaluate it right now, but the important point here is that this is not equal to 0. Okay, because remember E1 is a projector, is proportional to a projector which is perpendicular to the state ket 5. Okay, it has the state ket 0. Sorry, I'm very sorry for this. It has the state which is containing ket 0 and ket 1, both of them, right? So it will have some non-zero value. Right now we don't need to worry what the value is. Okay, so some non-zero value. Moreover, if I am given the state ket 5, then I can evaluate the same things as well. And in this case, I will see that the probability of getting E0 is non-zero, whereas the probability of getting E1 is completely 0. Okay. So now let us analyze the different cases. Okay. So I have the clicks corresponding to either E0, E1 or E2. Okay. You can also evaluate probability E2, which is again some non-zero value here, as well as some non-zero value here as well. Okay. So let's say if the first outcome clicks, okay, I know the first outcome could never click if I had the state ket 5. Okay. Uh, Sorry. Suppose I get the outcome click corresponding to E0. Then I know from this particular relation that the state could not have been equal to ket psi, because for E0 the probability to get a click in this particular case is 0. So that will never click. That means when I get the click corresponding to E0, I know the state was ket phi. Similarly, if I get the outcome corresponding to E1, then I know it could not have come from the state ket phi, because the probability of getting the outcome corresponding to E1 is 0. I will never get this outcome in my quantum measurement, but it could have come from the state ket psi. Okay, so in this case I again definitely know that my state was ket psi. I can also get an outcome corresponding to E2, and when I get this outcome, you will see for both of them the probability of E2 is non-zero. Okay, so we cannot say whether it came from the state ket psi or from the state ket phi. So in this case, we will just say I don't know. Okay, it could have come from either of them. Okay, but as you can see, whenever we get the outcome E0 and E1, we are able to perfectly distinguish between ket phi and ket psi. When I get the outcome E0, I can say, okay, the state was definitely ket phi. And when I get the outcome E1, I can say definitely the state was ket psi. So this is with certainty that I know for these two outcomes only that what my state was. Only for the third outcome, I don't know. Okay. Now coming back to this parameter S that we had here. Okay. And moreover, while defining the observables E0, this is chosen in such a way that we want to minimize the probability of getting the third click corresponding to E2. Okay, we want to minimize this. We want to minimize the probability of such a situation where I don't know what my outcome is, whether it is corresponding to ket phi or ket psi. Because if my probability of perfectly distinguishing between psi and phi is high, right, then I am doing my task in a very nice manner, right? However, if my probability of distinguishing between them is low, then I am not able to do that all the time. Okay, so in this particular case, we are able to distinguish ket phi and ket psi perfectly, but only in some cases. but only with some probability. So whenever we get the outcome E2, we will not know whether the state was psi or phi, but whenever the other two outcomes click, we will definitely know what the state was. Okay. So here the question could be asked, why we have designed a measurement which has three outcomes. Okay. So we have a POVM which has three outcomes. So we can ask ourselves, why limit ourselves to just three outcomes? Why not have four outcomes? Why not have five or more? Right? So the idea here is we want to have a measurement, an outcome E0, which will tell us whether the state is phi or not. We want to have the outcome E1, which should tell us whether the state was psi or not. And then we have a junk or a outcome for which we actually did not need this outcome, but because of completeness relation, we got this outcome. Okay, so we generally in information theory we call this outcome as the junk outcome. Okay, this outcome does not give us too much information, but this has to be there because of completeness, because the probability should sum to one. There should be some outcome. So if I look at this in in an optical scenario, let's say I have a detector D, okay, and so let me also make the detector. So let's say I have a photon which is traveling along a path, and I have a detector D. Okay, then what can happen is either the detector clicks, okay, and it registers, let's say, some outcome, and register an outcome corresponding to 0. Okay, or it registers an outcome corresponding to 1. Okay, but there could be another situation where I have, let's say, a polarizer, or let's say a polarizing beam splitter, and now I have a photon which has some polarization. I don't know what the polarization is. So with some probability it is transmitted, and with some probability it is reflected. So I can put two detectors here, right? So if this detector clicks, I can label this as corresponding to 0 0, or corresponding to horizontal polarization, and this one corresponding to vertical, right? So what I will say is, if I have a photon which is impinging itself on the polarizing beam splitter, either the detector D1 or D2 will click. But in an actual experiment, there will be scenarios where neither of these detectors click. Okay. So in an ideal scenario, what is happening is either I get the outcome HH or VB. So this is a projective valued measure, because you can see these are all, both of them, projectors, right? So in an ideal situation, this is what I will get. Okay. But in an actual experiment, what will happen is there will be cases where both these detectors do not click. Okay, so I am sending a photon, but the detectors are maybe imperfect, or maybe because of some background noise or whatever, or maybe my electronics is flawed or whatever. The detectors do not register the photon. Maybe it impinged itself on the D1, but maybe it did not register that photon as such. Maybe the current was not too high, or maybe the avalanche did not happen, or whatever. Whatever may be the reason, and there will be reasons. This will happen in the experiments. So in the non-ideal case, we will have a situation where D1 and D2, both of them don't click. So what we can do is we can ascribe that as a different outcome. So with some probability P1, we will have HH. With some probability P2, we will have the outcome corresponding to VB. And with some probability P3, we will have an outcome. We can label that as perp. Okay, which states that both detectors did not click. So as you can see here, we now have three outcomes. Moreover, this is no longer a projective valued measure. As you can see, the operators that we have, for the measurement operators that we have, they are no longer projective projectors, and as such, this is now a POVM. in the non-ideal case. Okay. So last thing, let us look at the state update. So once we have implemented the measurement, remember the black box device that we had. We had an input state as well as an output state. Right now, we have not talked about what is the output state. Okay. So let us look at what is the output state, irrespective whether I am measuring a POVM or whether I am measuring a projective value measure. The rule to update the state or get the output state remains the same. Okay, that will not change. The rule will not change. Just like we have the bonds rule. Okay, the rule does not change, but the operators that we are using in the bonds rule, that will change. Okay, so here that something similar will change. So consider any measurement mu, which is given by E0, E1 up to En. So this could be PVM or POVM. So if it is a PVM, EI square is equal to EI, and if it is a POVM, then in general EI square is not equal to EI. So we are not imposing any condition whether it is PVM or POVM. Okay. So what we need to do is, for each of these operators EIs, we need to decompose it into this following form: MI dagger, MI. So we need to figure out two measurement operators, MIs. Okay. So these are in general called as cross operators or measurement operators, depending upon what context you use. I mean, sometimes the definitions or the denotations are used interchangeably. Okay. So the best idea to find these MIs is just take the operator EI, okay, and take an under root of that operator. So when we are taking an under root of the operator, what does it mean? We diagonalize the operator, we find out its eigenvalues, and then just take the under root of the eigenvalues in the diagonal form. Okay. So this is just one description. Okay. It does not mean that this is unique. So in general, these measurement operators, they're not unique. There are infinitely many of them possible. Okay. So for example, I can have a measurement operator Mi equal to e to the power iota theta under root ei, where theta could be any parameter. Okay. And as you can see, ei is still Mi dagger Mi. And I can choose any particular value of theta. Okay. And it will still satisfy this particular equality. Okay. So this is just one description of finding them. Generally, finding them is you can find them based on just by looking at the operators themselves. So if you have projective value measurements, you can just take the under root very easily. It is just equal to the projector that you have. Otherwise, it is generally very not that difficult to find. Just take under root of e, and if you want to impose some non-uniqueness, you just impose a phase factor in front of it as well. But remember, this is not the only description. There are infinitely many of them. Okay. So once we have found these measurement operators, then we need to say if outcome E0 clicks, then the state at the input state was rho, then the input state is then transformed to a final state, let's say rho naught, which is equal to m naught dagger rho m naught divided by the proper normalization. So remember, the state has to be normalized. Okay. So that is why we have the denominator factor, which normalizes the state with its probability. So if you look at the denominator, it is nothing but this is equal to trace of E0 rho, which is nothing but the probability of getting that particular outcome. Okay. So we are just renormalizing the state that we are getting. Okay. The main description of how the state changes is given by m naught dagger rho m naught as mentioned here. If we got the outcome E1, then the initial state rho transforms to rho 1, which is m1 dagger rho m1, and then again renormalizing it once again, right? And we can keep on doing this so on and so forth for En, and rho transforms to rho n, which is equal to mn dagger rho mn, and then again renormalizing, right? Now, let's say you know which outcome clicked, then you can just use the state update rules as given here. Let's say you know, okay, the EI outcome clicked, then you just evaluate a row I via the same rule. Okay, but let's say where you are using some measurement, you are noting down the outcomes in your register. Okay, but somehow you lose the register. Okay, so you noted down, okay, when I first ran the experiment in the first round, I got the outcome corresponding to EI, and in the second round, I got the outcome corresponding to EJ or whatever, and so on and so forth. Okay, so for each particular round, you know, okay, this was the updated state or the output state that I got. Okay, but let's say you lose the register. You don't have any information about in the first round of the experiment whether E1 clicked or E2 clicked or whatever. You have lost that particular information. However, you only know that these were the particular outcomes that you had: E0, E1, En, and so on, so forth. Right? So this is the only information you know. Moreover, you know that on an average, like the state update corresponding to each of these outcomes is given by these particular rules. Okay. So based on this knowledge, once you don't have the knowledge about what outcome click, so this is only when you don't know which outcome clicked. Okay, so this is only in that particular case. Then the initial state transforms into a state rho prime, which is just taking a average value of all EI, MI, dagger rho, MI, and we have taken the state update corresponding to each outcome I, and then just taken an average by multiplying it with the appropriate probability and summing over all I, right? And this is nothing but equal to, so remember the denominator is just the renormalization, which is equal to Pi. This cancels out, and we have summation I, Mi rho, Mi, right? So this was the state update. So I will stop here now, and if there are any questions, please let us know. So there was one question: what is the value of theta? So here, this value theta could be anything. That's what I'm saying. You can take arbitrary values, and you will get arbitrarily different MIs. Okay, but the corresponding operator EI would still remain the same. So that was the intent of having e to the power iota theta here. What is MI dagger? So MI dagger is some measurement operator which we call as measurement operator or a cross operator. Okay, such that this particular relation holds. EI is equal to MI dagger MI. Okay, and these MIs, they are in general not Hermitian. Okay, there could be arbitrarily many descriptions of MIs. Okay, this MI, okay, which will give you the same capital EI operator. Okay, so as I mentioned, if you take this particular definition, then for many different values of theta, you can get the same EI, capital EI.
I think these are the only questions you already addressed. So over to you, Avasti sir.
Sorry.
Okay, so no other questions, sir. Thank you very much
Okay.
for your time and this elaborative lecture. So much mathematics. I hope the participants have enjoyed the lecture, and you are also continuing tomorrow.
Yes.
So if there is anything, so I encourage participants, please feel free to interact through the chat, or you can raise your hand. You may interact with the speakers. So on behalf of participants as well as on my personal behalf, I thank you, Dr. Jaskaran, for
Thank
today's lecture. And looking forward to meet you tomorrow for this lecture.
Sure.
Once again,
Thank you,
very
sir.
much.
Thank you very much. Okay. Bye-bye.
Okay, bye.
Thank you, sir. So dear participants, the speaker will be continued for tomorrow also. So you can take the lectures from YouTube also as a revision site, because it will be a continuous, all lectures are for measurements. So it is beneficial for you. The YouTube lectures you can attend from there, from the AICT Academy. Thank you.
Deepesh, could you check please this login? I will send
Okay.
you. Okay, any problem. I will send you the WhatsApp. No problem.
Okay, sir.